So the problem I had asked last time was, so this is the baby version, it's a simple version, is show that every odd degree polynomial is eventually monotonic. So here when I say odd degree polynomial, I mean from R to R. Okay. Or you can also say polynomial in with real coefficients and real inputs. Or let me just write eventually injective. So would someone like to first rephrase the question in more concrete terms? I had said this last time, but if you can rephrase it in some other way also. Basically, you need to expand on the word eventually. Anyone? Yes, so you are also giving an answer, which is correct, right? Okay, so then let me just rephrase it. Okay, let's just rephrase it. I think we all understand it. So basically what we want to show, show that there exists an interval, no, or m comma minus m, whatever. Let me just say there exists an m, there exists m such that let's just call this px or degree, such that px, if you consider it on R minus this region, this is not just just this part of the real line. This function, we're looking at this as a function, right? Polynomial taking inputs and giving output. This to R obviously is injective. This is what the question is. And then the claim that is being made, let so yeah, let me not say any intuition. You will. Last time you said that it's eventually subjective. No, not eventually subjective. It's obviously subjective, right? There is no. Yeah. Right. Okay. So let z naught B. But that is not a proof. You have to, right? That is not a proof. Right? Okay, so let Z not be a real root, the real root with largest magnitude. So it could be negative also. Okay, you have to take care of all that, but it is simple enough. Okay, so if let's say Z0 is a root here, but why am I saying Z0? I should just say X0, right? Because otherwise X0 is here, and then there are some other roots like this, maybe. Okay, but as you can see, this is the root of largest magnitude. Now, the claim is that the graph is, the claim is that on this region, it is monotonic. Now this I have not proved. It's simple to prove. Please think later if you cannot see it immediately. So after the last positive roots is monotonic, and after the last negative root also it is. This is also monotonic. And because one is positive and one is negative, IVT. Okay, can you expand? It's a little more than IVT. It will be on the same sign. Yeah, that's okay. Yeah, but what we also want to show monotonic. Okay. No, it won't be the opposite. Yeah. So I think, yeah, Rasavru, I think you get it. You can show injectivity. Yeah. So I'm leaving this. This is easy, but just show it. You have to show injectivity, monotonicity, whatever you have to show. So you can show monotonicity here and monotonicity here. And then because it's odd degree, it will have opposite signs. And so it will imply injectivity. Okay. See, this will not work for even degree. Even degree, it will maybe go like this. You can forget about this, right? Then also it will be monotonic here and monotonic here, but it will not be injective because obviously not, right? The values are coinciding, this, and so on, you can see. So odd degree is, no, you can't control the magnitude of the roots, right? It's just a real, same. No. No, it's an odd degree polynomial. F of x is not equal to f of minus x or anything like that. It's not a, it's not all the powers are odd, or it's not function. Yeah. Okay. So this was a rather simple question, right? This is very simple. But now, if you think about general, please, if you don't see why it's monotonic, try to see it. It's not hard, but think about it. Note it down. But now, the polynomial is from C to C. Now it's a question mark. So like a part B, that's the same hold for every odd degree polynomial. So the degree of a polynomial, whether it's odd or even, does show a lot of variation if you're looking at from reals to reals, right? The degree, because the degree, affects the sign and there is positive and negative and so on. But what about C? So try to answer this, or if you are not confident, try to first phrase it and tell me this how to say this precisely. No, the coefficients may also not be real. They can be real. Still, it's a polynomial. C. P is a polynomial from C to C does not mean that the coefficients have, they can still be real, obviously. But now we are not insisting that they be real. Usually we don't think of polynomials from complex numbers to complex numbers. I mean, whenever we think, we just think of roots and such. Yes? Right. So anyone has a model, how you would try to visualize such things? It may not be necessary for this question, but definitely it's necessary for a lot of other questions. And just important, I think. Okay, so since no one has a clear answer, I want someone to first phrase it properly so that everybody can think about this clearly, or at least have one clear way to think of. So let me then phrase it. You want to say that there is an R, okay, such that this function pz, if we consider it from C minus the disk centered at the origin with radius R, this is injective. And about visualizing, I will just leave it at very primitive stage and just say that you can just take 2 copies. And it's actually a pretty powerful visualization if you try to build on this via examples. And okay, just take the domain and just like this, you can understand with range. Okay. There are other beautiful ways to visualize, but for now we can just keep. So basically, I'm saying that there is a disk So obviously, it's certainly not injective. So it can never be completely injective, right? Does everybody see that? I mean, unless it's a linear function, it's never injective. So this is a slightly new question. If I don't put the eventually condition, then the answer to this is clearly no. Yes, right? I mean, you have to say a little bit more, but it's more or less that. Would you or anyone like to explain it? Right? No, okay. But yes, no, but even then, your reasoning is incomplete. So, okay, there is 1, 0. What is the polynomial? So, okay, if other than linear, still think. Uh-huh. Yeah. So then what's the case that you're missing? What's the case he's missing? So see, your argument is based on the fact that there are two distinct roots. Yeah. So the only case you need to consider is when all roots are same. Right? So if P has two distinct or at least two, means this case is trivial. Right? But if, and these multiple roots are a real headache. I mean, they cause real problems in all sorts of things. Okay? But here, let's see. So if, so this side and that side. That is that is the thing, right? You have to say it in the no, because in the real it doesn't create a problem sometimes. Right? So I think all of us were wrong. What I was saying was wrong. So let's write it clearly. So if all roots are same, sorry, let me write this properly. See, first thing to notice is we only need these two cases, right? If you write it clearly, P has two distinct roots, your reasoning is done. Yeah, this implies not injective. So we don't need to consider like a multiplicity, that means the different nuances. Just these two broad cases are enough. If all roots are same, now let's try to think about this case. In this case, how do you say it's not injective, or what do you say? So what? Yeah. Yes. So I'll write it as z minus z naught or raised to n. Okay. Now you want to show this is not injective. So it is injective at 0. Earlier we were using the leverage of 0, right? That there are several pre-images of 0. Now, or rather several, yeah. Now 0 has only one pre-image for this polynomial. So we have to do something else. Turning point. What do you mean by turning point? No, but you should define turning point, or you should try to rephrase the word turning point. I get what you're saying, but uh-huh. Chandan, so yes. I think something like that, but I want to say, Chandan, so is that what you think, or say it clearly? Oh, okay. So you're saying that that's a turning point, right? But you see, that will not apply here because see, when you draw a horizontal tangent, you are using the model that your entire graph is in one plane, right? Here, the input is from one plane and the output is in the other plane. So that model doesn't work. Hmm. In fact, this is not true in R2R. You can just, everybody knows, right? I mean, if n is odd, we can just take this to be a number, it doesn't matter. Just take 13. If if we take this from R to R, it is actually injective. And that exactly, you can just see that where the turning point happens is actually monotonic at the turning point. Well, in this case, it will happen at some x naught, yeah, some x naught, but the same thing, same geometry. How do you reason in C to C? So we are down to this case of injectiveness, not eventually injective, but just injective. So you can just think about this particular PZ. Okay? I mean, you guys already understand the Z naught is not important, but I'll not say anything now. Let's first you think. Mm-hmm. But this is Z minus Z naught. Uh, some. Mhm. Yes. Okay. Yeah. Hmm. Hmm. Right. And if you have distinct roots for that equation, then you would have proved that it is not injective. Yeah. Right. So yes, that's a plan, and that will certainly, but that can get, it will work. But see, you can try that and it will work. But see, you can just say that you can, instead of considering pz, you can consider p z plus z naught, right? See, whether pz is injective or pz plus z naught is injective, these are equivalent questions. Right? And this is the first step that we should do. We should, because C is not a geometric thing completely. It has arithmetic. So we're basically using the arithmetic to simplify the question. Okay. So this is basically the QZ. So now you need to basically ask, is this an injective function? But then everybody knows roots of unity, right? It's not injective, right? Because QZ equal to 1 has 13 roots. There are 13 different things that map to 1. Right? So it was simple. And basically what you are doing, you would also basically get there in a more roundabout. Yeah, the other routes you analyze, but it just will take a bit more time. Some okay. So this is, so answer is no, it is not injective. Okay. So basically not injective is coming because everything has roots, right? No matter what you take, everything has roots. So now please try to answer the question of eventually on your own. Okay, this is a problem for homework. I mean, if you already see it, don't say it now. But yeah. So this is not. So we have found an example which is not injective, but maybe it is eventually injective. So you have to think. If you know it, then don't say the answer. But is this solution that we have discussed, is this clear? Okay. Yeah. So this question arose out of some question which I was doing, and I wanted this to be true. Okay, but then it would make the solution, it would make my approach something very easy, but it was not true. Okay, and this is a completely elementary question that just all of us know and understand, and it's also be a good mix of things. But here you see something very interesting. If you or you can just take this thing. Okay, if you take z naught, you see this point z naught is getting mapped to the origin, right? This point z naught is getting mapped to the origin. No other point is getting mapped to the origin, right? Z naught is getting mapped to the origin, but no other point is getting mapped to the origin. That's basically what we see, that there are no other distinct routes. There are no other routes. But if you take any neighborhood around Z0, okay, if you take any neighborhood around Z0, and yeah, you just take any neighborhood around Z0, or rather, just give me 1 second. Yeah. Yeah, if you take any neighborhood around Z0, then you find 13, then you find 13 points in this neighborhood which map to the same point, right? 13 points. And you know how they will be distributed. A regular polygon, right? There will be 13 points which map to some one point. Roots of, they will not exactly be roots of unity. If you translate and such, it will be, you have to translate and you have to, yeah, but the radius may not be one and center may be different, but yeah, but you understand, right? So a lot of things will get mapped to the same thing. These 13 things will get mapped to this. And every point in that every point in that neighborhood has 12 other such partners. Right? So there are sets of 13, 13 in which that is partitioned, and 13 move to one, then another 13 will move to the same image, another 13 will move to the same image. Is that clear? Is that okay with everyone? Yes. Yeah. So yes, yeah. So basically, if you have a Z1, let's say the Z1, so I'm taking an arbitrary Z1, it is in a small neighborhood, and now any neighborhood you can take, just it has to be a circular, otherwise it will not work. I took a Z1, so let's call this ball B. I took a Z1 inside this ball, right? And let's say you take the image of Z1, this is the image, right? We all know this is the image. But if this is the image of Z1, then doesn't it have 13, doesn't this have 13 pre-images? Right? This is the image, right? This is P of Z1. I mean, it's already here, P of Z1. I mean, whatever this is, it is some complex number which is not zero. It is not zero. That's the point, right? It is not zero. You can just call it some, just for convenience, you can just call it some W. Now, obviously, there are 13 pre-images, right? Just to solve the equation, 13 root of unity. It has 13 pre-images, right? One of them will be Z1, but there'll be 12 others. There'll be 12 distinct others because you'll have 13 roots of W plus Z0. Okay, and this happens for every point Z1. So this is a good property, which is easy to prove, as we have kind of proved. There's something very amazing going on, that there is one point which maps to one point, which only has one image. But then if you take, no matter how small a ball you take, there are 12, for every point, there are 12 other things which map to the thing. So at one point it is injective, kind of, right? And then the other points it's the same degree of non-injectivity. So this one point, it's kind of exceptional. This one point, which Z0, which maps to 0, is very exceptional. Okay, now it has names and it has a lot of usage, but that I'm not saying. We don't need that now. So this is a simple property that you prove. Okay. So any questions? Now you see you could actually shift the origin. So you could make a change of coordinates. And then this function would look like z to the power 13. So under a change of coordinates, this function is z to the power 13 around that point, right? Okay, around that point, it is z to the power 13. Okay. Now here is a question that you guys should try. Let z1 be in the ball. So z1 is just a point which is in the ball. Some other point, z1 is not equal to z0. Okay. So what did we show? That around z0, no matter what ball you take, it is not injective. Right? Around z0, right? Around this point z0, no matter what ball you take, there are 13 things in that ball which map to the same, and some other 13 which again map to the same. So you cannot make it injective no matter how small a neighborhood you take. It's the opposite of eventually injective. Now I'm asking a question about locally injective. That will be, take a point z1. I mean, you can take z0 to be 0 and do your problem. Okay, that's completely fine. It's the same thing, but you can take it to be 0 if you want. Take z1 which is not equal to z0. Okay, now I want you to show that there is, I could just say locally injective, but there is a ball b1 around z0, around z1, okay, such that this polynomial on this ball is injective. And this is related to the fact that the 13th roots of unity have some distance between them. There is a precise distance, angular distance at least. So you can exploit that. Yes, so you have to exploit that. Okay. Obviously, that ball around Z0, you don't want it to include that ball around Z1. That ball around Z1, you obviously don't want it to include Z0. If you include Z0, you are gone. Okay. If you take a small enough ball, but it has to be small enough so that, yeah, you have to think. It's not difficult. It's a very geometric thing. You just draw your pictures. It's completely geometric. Okay. It's almost like a geometry question. So we were talking about eventually injective. Now we have two questions, one about eventually injective and another about locally injective. Okay. So we are basically, what we have basically learned is that if you take the function this z going to z to the power n, then 0 goes to 0. And 0 is the only point that goes to 0. Nothing else goes to 0. But if you take any small ball, then there are n points that, are mapped to the same point. There are n points in the domain, obviously. In any small ball, you will find n points which map to the same point. And like there are, groups of n points always in any small ball you take. And The example of such a function we have seen is z going to z to the power n. This kind of situation, okay, where f is a function from c to c, okay, and 0 goes to 0, okay, but then for any ball around 0, there are n points which map to the same point, and there are n other points which map to the same point, and so on. We have seen that z to the power z going to z to the power n is an example. But then the claim is that this is the only example. There is no other function like this. But that I'm not asking to prove. In some sense, this is the only example. Obviously, you can make bad functions, but like good functions, like differentiable functions, this is the only one. But that we are not going to do. And that's the usefulness of this analysis. But for us, it's just a problem. Okay, so note down these questions, which I have, okay, you can see it later, but note it down, it's convenient, and try it. Then we move to a new. So I'll erase. Okay. So yeah. This question didn't have much calculus or anything. We didn't really. But here is another question about polynomials, which has calculus. Okay, so let's do this because these are some maybe unique kind of problems. So I'll just give it a name and then I will explain. Okay, so continuity of multi-valued function. But it's just fancy names. I'll just explain. I mean, in full generality, it is a fancy thing, maybe, but we're just doing a simple version of it. Let's take an example. Let me give an example.